All right, let's talk about something that's at the absolute heart of how any program thinks and acts: conditionals and loops. This is where code really starts to get smart. Think about a roller coaster for a second. It doesn't just go in a boring straight line, right? It twists, it turns, it drops. And a computer program? It's a lot like that. It's not just a simple list of instructions to follow in order. It has to make decisions. It needs to choose which track to follow depending on what's happening. So how does it do it?
Well, the very first tool in our toolbox for making these choices is the if statement. Just think of it as the simplest fork in the road your program will ever see. It asks a quick question, and based on the answer, it either takes a new path or it just keeps chugging along.
Now, that little question the if statement asks, that's called a conditional. And here's the absolute key. The answer can only ever be one of two things: true or false. That's it. In the programming world, we call this a Boolean value. It's a beautifully simple concept. Is the light green? True. Is it red? False. That's all the computer needs. Okay, so let's look at some real code. First line, super simple. We're making a variable, we're calling it x, and we're storing the number 6 in it. Then comes our if statement. If we translate this to plain English, it's just asking, hey, if the number inside of x is greater than 5, then go ahead and print whatever's in x. See, it's a pretty direct question. So what's going on inside the computer's brain here? Well, it takes that line, if x greater than 5, and it just boils it down to that one simple question: is x greater than 5? And since we know x is 6, the computer's logic gets a crystal clear answer: true. And because that answer was true, the program gets the green light. It goes ahead and runs the code that's indented right below it, the print x line. And what's the result? The number 6 pops up on the screen. It's a perfect little chain of cause and effect. But yeah, that brings up a really good question. What happens if the answer is false, if the condition isn't met? With a simple if statement like we just saw, the answer is, well, nothing. The program just skips that indented part and moves on. But what if we want to give it a plan B, an alternate set of instructions? That is exactly where else comes in. It's the otherwise path. Let's look at this new version. This time, x is 4. The program asks the exact same question: is x greater than 5? But this time, the answer is false. So the program completely ignores the first indented line, and instead, it jumps straight down to the else block and prints below 5. And here is the most important part about if-else. It's a guarantee. One of those two paths, and only one, is going to run, every single time. Okay, so we've got this simple fork in the road down. But let's be honest, real life is rarely that simple, right? Sometimes you're not at a little T-junction. You're at a massive intersection with roads going in all different directions. So how in the world do we handle that in our code? An if-else statement is great, but it only gives us two paths, an A or a B. What happens when we need a C, a D, and maybe even an E? And here is our brilliant solution: elif. It's literally just short for else if, and it lets us chain as many checks together as we want. In this fun little example, our program is trying to identify a rabbit. First, it checks if the rabbit is Roger. If not, else if it's Bugs. And if it's neither of those, the final else is our catch-all for, a killer rabbit. So let's trace the computer's logic here, because it's super methodical. It always starts at the top. Step 1, is x equal to Roger? Nope, that check comes back false. So it just moves down to the next condition. Step 2, okay, well, is x equal to Bugs? That also comes back false. So now, since it's run out of if and elif questions to ask, it has no choice left. It has to run the final else block. And the result is exactly what you'd expect. The program prints run. This whole structure is incredibly powerful because it checks each condition in order. But, and this is key, it stops the second it finds one that's true. Only one block of code in that entire chain will ever run. Okay, so we can make choices, we can handle multiple paths, but things can get even more complex. What happens when one decision actually depends on the result of a previous decision? Well, that's when we start layering our logic, putting decisions inside of other decisions. This is called nesting. In this example, you can think of the program like a host at a fancy restaurant. The first big question it asks is the age 21 or over? Only if the answer to that question is true does it even bother looking at that inner set of questions about the activity.
If that first age check fails, it jumps straight to the outer else block, says you are underage, and completely ignores all that inner logic. You know, sometimes you need to ask more than one question at the exact same time. For that, we've got these two little words, and or. Now, the difference is absolutely crucial. And is super strict. For it to be true, every single condition connected by and has to be true. Or, on the other hand, is way more relaxed. You just need one of the conditions to be true for the whole thing to be true. And this one puts it all together. It's some pretty complex logic to figure out if a baseball player is an all-star. Let's walk through it. The first if check fails, so we drop into that big else block. Inside, we hit our nested check. Does the player have over 40 homers or over 150 RBIs? Nope. So we go to the elif. Now this one is strict. It uses and. It asks, is the batting average over .300? And are home runs over 30? And are RBIs over 100? All three of those have to be true. This is a perfect example of how you can translate real-world rules directly into code.
All right, we have totally mastered making decisions. Now for the other fundamental superpower of programming, repetition. I mean, what if you need to do the same thing not once, but hundreds or even thousands of times? You're not going to write that code 1,000 times. No way! You use a loop. The most common kind of loop you'll see is a for loop. It is designed to go through a sequence of items, like all the numbers in this list, one by one. The goal here is simple. We want to add up all the numbers. So we start a total at 0, and we let the for loop do all the boring, repetitive work for us. Let's just watch it work. On the very first pass, the first iteration, the loop grabs the first number from the list, which is 2, and it puts it into that temporary variable called num. Then it runs the indented code. So our total goes from 0 to 2. Okay, once that first pass is done, the loop just automatically circles back to the top and grabs the next item, which is 4. The num variable is updated to hold the number 4, the code runs again, our total was 2, now we add 4, our new total is 6.
And you can see where this is going. The process just repeats. Next, num becomes 6, total becomes 12, finally, num becomes 8 for a final total of 20. And here is the beautiful part. The loop is smart enough to know when to stop. Once it's processed that very last item in the list, it just finishes, and the program carries on. And that's really it. Between conditionals like if, elif, and else for making all your decisions, and for loops for automating all the repetition, you now have the core building blocks to control how your program flows. These are the tools that take code from being just a simple script to being a smart, responsive, and really efficient application. So with these tools, you're the one who gets to draw the map. You define all the possible roads and routes your program can take. The logic is all yours to design. So really, the only question left is, what are you going to build?